Okay, now we're going to talk about the Koch snowflake. Okay, so one of the earliest and most famous fractals to be described using the iterative process in the previous section is the Koch snowflake, pronounced Koch, right? Just like I said it. This figure is named for the Swedish mathematician Helge von Koch, who first studied it in 1904. We'll start by describing the Koch curve on which the snowflake is based. So the way it works is you have the initiator, which is just a line, okay, and then the generator. And so this is just to create the iterated fractal. Okay, so notice the generator is we take the middle third, right? So basically they're all equidistant, right? So we take the middle third of the segment, right? And what we do is we replace it with an equilateral triangle so that all the new, so we have now 4 line segments that form an equilateral triangle, if you will, with these 2 line segments. So we actually have 4 line segments that are all the same length. Okay. And so that's the way we generate the Koch curve. So notice in step 1 we have this. Okay. And then each face each segment we're going to do the exact same thing. So we're going to do the same thing on this leg and on this leg and so on, just like they're shown with the arrows. Okay. And so we end up with this. And then we're going to continue the process with the same way. So now on each one of these legs, right, we're going to do the same thing. We're going to do this. And so we're going to replace each one of these legs with that. And so when we do that, we get step 3, which looks like that. Okay, and this is the Koch curve. Now, for the Koch snowflake, that's basically what we're going to do. Now, we'll get to the Koch snowflake in a second here. So it says, notice that since step 0 only had 1 line segment, step 1 only required 1 copy of step 0. Okay. Since step 1 had 4 line segments, step 2 required 4 copies of the generator. And then step 2 then had 16 line segments. So then in step 3 required 16 copies of the generator. Okay, and then step 4 then would require 64 copies of the generator. Okay. So notice that it's a multiple of 4 each time. The shape resulting from the iterating this process indefinitely is called the Koch curve. Okay, and that's what this shows. Okay, now that we understand the Koch curve, we can easily describe the Koch snowflake when we start with not just 1 line segment, but we start with an equilateral triangle. So now what we do is we start with an equilateral triangle where we're now going to, on each side of this equilateral triangle, we're going to start doing the Koch curve with the generator. Okay, so on each side, as you can see, when we do it 1 iteration, we get this. And then we get 2 iterations, we get this. And then the 3rd step or 3rd iteration, we get this. and so on and so forth. And as we repeat the process indefinitely, we end up with what's called the Koch snowflake, which is this right here. And if we were able to zoom in to one of these parts, we would see the same thing keep going on. Okay. Of course, we cannot really repeat the process infinitely many times, but even so, we can deduce some interesting properties of the completed Koch snowflake. First, if we zoom in on any section of the snowflake, we will see the Koch curve, right? That's what I was just saying a moment ago. And the Koch curve is perfectly self-similar, like we were talking about in the last video. Okay, so again, if I zoom in on this segment right here, what we're going to do is we'll see the same thing continue. The same process. Okay. Second, it's clear from the generation rule that the perimeter of the snowflake increases with each step of the construction. Moreover, we can describe precisely how it changes. At each step, we replace a single line segment with 4 smaller line segments. Each has 1/3 the length of the original segment. That's what I was getting into at the beginning, right? Thus, at each step of the construction, the perimeter will be increase by a factor of 4/3. Okay? Because we have, let's say, one line segment is 3/3, let's say, right? And so what we're doing is we're taking that third and duplicating it and adding another line segment that's the same length. So instead of having 3/3, we end up with 4/3. So to better understand this, let's let P sub n represent the perimeter of the snowflake at step n, where n equals 0 corresponds to the starting triangle. Okay? Then the remarks above tell us that the perimeter at any given stage is given by the formula, the recursive formula of Pn plus 1 equals 4/3 P sub n. So the perimeter of the n plus 1 figure is going to be 4/3 times the perimeter of the previous iteration of the figure. This says that the perimeter at any step is about 1.33 times the perimeter of the previous step, which is what I just said, right? To get an idea of just how fast the perimeter is growing, let's assume that the starting triangle where each side has 1 inch, so that the starting perimeter is 3 inches. Let's do that. So at the step 0, which we have the equilateral triangle, it'll be 3 inches. And then in step 4, it'll go up to 4 inches. Or excuse me, step 1, it'll go up to 4 inches. And then step 2, it goes up to 9.33. And then it goes to 12.44. And then it goes on until we get to 100, and then it's huge. Right? So just in 100 iterations, we're at a very large perimeter in inches. Okay? Now, we can see that this is going off to infinity, right? I mean, it makes sense. As n is increasing, the perimeter is increasing much faster. Okay, and the perimeter, just even after 100 steps, the perimeter of the partially completed snowflake is about 9.3 trillion inches. This is more than 1.5 times the distance from the Earth to the Sun, and the perimeter will continue to grow without bound. In other words, the perimeter of this completed Koch snowflake is infinite. It has an infinite perimeter, which is interesting to think about. On the other hand, the area. Now think about the area here, okay? The area enclosed by the Koch snowflake is finite. We can see this because of the circumference, or excuse me, if we circumscribe a circle around the starting triangle, the same circle will circumscribe the completed snowflake. So we know that the area will always be less than the area of that circle. Okay, since the snowflake fits into a circle of finite area, it makes, obviously we can deduce that the area of the enclosed snowflake must also therefore be finite. Okay, using techniques from calculus, we can actually show that the area enclosed by the completed snowflake is exactly 1.6 times the area of the starting triangle, which is also kind of cool. Thus, the Koch snowflake is a curve with an infinite length that encloses a region of finite area. So in summary, these are the properties that we have for the Koch snowflake. 1, if P sub n is the perimeter of the figure at the nth step, then the perimeter of the figure at the next step is 4/3 times P of n, P sub n. 2, because the perimeter increases without bound, the perimeter of the completed Koch snowflake is infinite. The area of the completed Koch snowflake is at 1.6 times the area of whatever the initial equilateral triangle is. All right. So now, the triad. Suppose that the starting equilateral triangle for a Koch snowflake has a perimeter of 6 inches and an area of 3.46 square inches. What is the perimeter of the figure after the first step of construction? Okay, so the way we do this, okay, it's the first step of construction, right? So it's 6 inches. So the perimeter, so we'll say P1. So P1 would be what? It'd be 4/3 times P0. Which then, of course, will equal 4/3 times 6. And of course, that will equal 8. So it'll equal 8 inches. And then it says, what is the perimeter of the figure after the fourth step of construction? Well, let's think about this. So if P1 is 8, P2 would have to be 4/3 times 8, which would be 32/3. And then P3 would be 4/3 times 32. So 32 times 4 is 128 divided by 3. Right? 32 times 4, that's 100. Yeah, that's 128 divided by 3. And so then P4 then would be 128 times 4 divided by 3. And so 128 times 4 is what? 480. 512 divided by 3. I believe that's correct. Okay. I don't know what the approximate is going to be, but I believe that that's going to be, so I believe it's going to be 512. So yeah, so let's do, oh wait, hold on a second. No. I'm sorry. I miscalculated. So let's do it again. So 8, right? So P1 is 8. P2 is 32/3. Right, okay. 32/3. So P2 is 32/3. P3 is 128 ninths. Yeah. 128 ninths. And then it'll be 5, yeah, so it'll be 512. 512 over 27. And then what is the area of the completed snowflake? Well, the area of the completed snowflake is going to be 1.6 times the area of the original triangle. So it'll be 1.6 times 3.46. Oops. Whatever that turns out to be. Okay, that's where we'll stop.